the point of this effort is to try to navigate using signals from FM radio towers, standard FM that we're listening to as we sit in our homes or driving around in our cars. And the idea is that if there's a roving receiver that is receiving these FM signals from all these towers and a base station that's receiving these same FM signals, and if the base station gives essentially single information to the roving receiver, and you form single differences at the roving receiver and also have a pressure altimeter, can you then navigate with the roving receiver based purely on these FM signals and aiding signal from the reference station at a known location and the altimeter? And so this is just part of that effort where we're trying to track the digital FM part of a signal. So if here's the signal at 92.3 megahertz from a station in the south. Here's the analog voice part of the signal, and these two sidebands are the digital FM signals, and they're encoded using OFDM techniques, which essentially are FFTing a bunch of signals that are QPSK encoded, and the symbol interval actually is just essentially one FFT batch interval with a little bit of extra because of the need to have some sort of timing guard bands. And so there are ways to basically take those signals in those bands and essentially deduce things like code phase and carrier phase. You have to do FFT calculations on them. You have to, in this case, we do essentially decision-directed decoding of the symbols. At least when we have our static receiver or roving receiver, we may aid with the symbols from the static receiver. And then there are all sorts of tracking loops, coupled PLL and F and DLL that track this signal, and these are described in the paper. So we've acquired a lot of signals and tracked them. And one of the first things we did was just look at static, both a static mobile receiver and a static reference receiver. We did the double difference accumulated delta range, basically from the carrier phase. And we saw that the precision of this is in meters. We saw that the precision of this is down around the 10 centimeter or better level. So we're hoping to use that accumulated delta range as the basic navigation observable. We also looked at double difference pseudorange. Double difference pseudorange should be 0, but it has a bias, and we believe that bias comes from receiver interfrequency bias. So this needs to be calibrated. And then you can see, even if we calibrate out that bias, there's a sort of a wander of the double difference pseudorange that, could be like 25 meters. So that's a lot less precise than this thing down around 10 centimeters. So we were going to look at this signal, but not necessarily hope in it for navigation. We also noticed in tracking the signals that we had some significant, this is now from a roving receiver driving on the freeway down in Charlotte, North Carolina. And we found that we had serious events. This is power, this is a beat carrier phase, or a change in beat carrier phase. And you can see we had these cycle slips during these power drops. We believe we're almost certain this is caused by multipath. We do have some algorithms that seem to be able to take out multipath or employing them. So again, these are all signal processing to get observables like pseudorange and accumulated delta range, and showing what we did with real data, what we were able to achieve, where we have challenges. At the end of the paper, we just look at, supposing we used our single difference pseudorange to try to navigate. And here we are comparing our solution with a roving receiver to GPS. And you can see we're like 400 meters off in the east position, up to plus or minus 50 meters off in the north position. And the vertical, has a bias of about 60 meters because our pressure altimeter wasn't quite right. So this is a problem. We believe this comes from the fact that we have these interstation or interfrequency biases in the RF front end filter. But this is a very crude navigation solution. This is not what we hope the best could achieve, because we think that the best, we're going to use the carrier phase and the associated accumulated delta range. We just haven't got there yet. That's a future work that Brian Schlossman, my co-author, is going to do. But we do think we have developed a good way of extracting pseudo-range and accumulated delta range observables, and we showed that pseudo-range observables are not that great for navigating, and the jury is still out on accumulated delta range. So I hope you enjoy the paper.